Okay, hello everyone. So in the previous video we talked about pressure in general. So let's talk about pressure in fluids. Now when we say fluids, it includes liquids and gases both, right? Gas and liquids. So pressure in fluids. So we know that in general pressure given as force divided by area. Now let's talk about the liquids first. Pressure in liquids. Let's say we have a container of water. So there's water in it. And so the pressure, this water, this liquid is creating a pressure, and at different places inside this container there will be different pressure values. When it comes to liquids or fluids, the amount of pressure depends on, like if you consider like a particular place, let's say the bottom of this container, right in the middle, somewhere here. The pressure at this point depends on the amount of liquid above that point. So in that case, if this is the point, the pressure is determined by the liquid, this height of this liquid that is above this point, right? So if you take another point like this, so let's say this is point 1, this is point 2. This point 2, the pressure is determined by the liquid above that point. So you can see this, the amount of liquid is less. The height of the liquid column, this height 2, this is height 1. Height 1 is bigger than height 2. The amount of liquid above point 2 is less than the amount of liquid above point 1. So the pressure takes the same manner, right? The pressure above point 1, P1, is bigger than P2. So the more the liquid, more the fluid above a given point, there's more pressure. Same goes with gases. A good example is our own atmosphere. The atmospheric pressure changes from place to place. At sea level, we have certain atmospheric pressure. If you go to high altitudes, like to a top of a mountain, there's less atmospheric pressure. It is because the amount of atmosphere above a given point changes from place to place. At sea level, you have the highest atmosphere above you. At the top of a mountain, like a very tall mountain, like maybe Mount Everest, the atmosphere is much less, so the pressure is less. So let's look into details. So let's talk about liquid pressure first. So let me draw another diagram. So let's say this is the water level. You can think of it as a lake or something, the surface, and here's the bottom, and there's water inside. So this is water here, so there's a fish to indicate there's water. So let's say we want to find the pressure at this point. The liquid pressure of a liquid is given by a simple equation: the height, the density, the gravity, right? So this is height of the liquid column, the density of the liquid given by rho, and g is the gravity. So liquid pressure is given by H rho g equation. Where is this coming from? This equation comes from actually pressure equals force divided by area. This is the starting point. Mathematically we can show that let's say you want to find the pressure at this point, so we take some area like this at that point. Let's say this is area A, and we want to find the force acting on this area. So it's, if you consider a column of liquid above that, now here's the column of liquid, we can find the weight of this column, right? Weight, or mg, that's the force acting on this surface area down here. So area. So how do you find the weight of this? If we know the volume of this cylindrical column, volume is area times height, and then we can find the mass, which is volume times density, so A H density, and the force, which is the weight of it, mg, so that's gonna be A H rho times g. So that's the force. So pressure is force divided by area, A H rho g divided by area, you get H rho g, right? So the liquid pressure comes due to the height of the liquid column multiplied by the density of the liquid multiplied by the gravity. So if you look at a different point like this will have a bigger pressure. This is somewhat pressure. If you look at a point like this will have even less pressure, right? Okay, let's move on. Okay, let's try a simple example. And again, these examples are all coming from the shared PowerPoints. It's in under files. So we have it says in a storage tank which is 30 meters above the ground level, there's water in a storage tank, and it's asking what's the pressure inside the house faucet. So we have the storage tank like this, an outdoor storage tank. So this is the ground level, and here we have a house, and there's a sink faucet. So let's say this is the faucet. Alright, so it's asking, now there's a water line coming from this storage tank to the house, and it says water is 30 meters, the water level is 30 meters above the ground, above the faucet. So if you measure from the faucet, this is 30 meters. The question is, what's the pressure at this point? Now, an important thing about liquids, these connecting lines, it doesn't need to be straight lines. It can have any number of bends, any number of angles, that's fine. What matters is the direct height. So for an example, if you have a water tank and then you place the faucet right under it, this is the faucet. I know it's a bad diagram, but have the idea. This is the faucet. It's connected like this, and the water column starting from here, it's all the way 30 meters. It's the same thing. You can have it somewhere else, but as long as the height is same, it's going to have the same pressure. So the pressure at the faucet is H rho g, 30 meters. Density of water is 1000, 9.81. So take the calculator and do the math. Gives you 294,300 newtons per meter squared, or we can set pascals, or you can set 294.3 kilopascals. Right? So this is how we find the pressure due to a liquid. Okay, let's move on. Okay, so the next thing I want to talk about is atmospheric pressure. The pressure in our atmosphere, the normal pressure around us. So atmospheric pressure is created, the reason behind atmospheric pressure is the weight of the gas, weight of the atmosphere around us. If you say this is the surface of the earth, it has this atmosphere, so here's some mountain, here's a person, so there's atmosphere above us, right, everywhere. This is the sea level, ocean. Okay, so depending on how much atmosphere above you, the length of the atmosphere, thus it creates pressure. So for above the person, we have a column of atmosphere about this tall. Top of the mountain, there's a shorter column of atmosphere. At the sea level, you have the highest amount of atmosphere above you. So that's why the pressure is highest. So less pressure, more pressure, highest pressure. If by some means you can go underground, let's say like a mining tunnel or something like this, much more atmosphere above it, right? So very high pressure. Okay, so atmosphere has a density, atmosphere has a mass, this creates the weight, so that creates the pressure. At sea level, we say that pretty much around the world it has very closely the same pressure amounts. So at sea level, generally we say that's where the highest pressure is. So the atmospheric pressure, or we sometimes write it as ATM, atmospheric pressure is about 1.013 times 10 to the 5 newtons per meter squared. 1.013 10 to the 5. This is called 1 atmospheric pressure unit, this many pascals. Sometimes we round it to 1 atm is roughly equals to 1 times 10 to the 5 pa. Also in the in atmospheric sciences, we call this the bar unit. 1 bar is 1 atm, right? So if you know the density of the atmosphere above you, the height of the atmosphere, you can do a simple math and figure out what is the atmospheric pressure is. So with that, I'm going to introduce a few more terms. So atmospheric pressure, I'm just going to write it as ATMP, sometimes denoted by PA, atmospheric, actually no, PO, sometimes denoted by little letter a, but I don't think it's a good idea to use two different things right now, so let's just say PO. There's another one called gauge pressure. Gauge pressure, denoted by PG. There's another one called absolute pressure. P or sometimes PA. So what are these terms means? Well, let's go back to this example, here we have a lake, and this is the bottom of the lake. Let's say this lake is 100 meters deep. Right, here's the lake, here's the fish. What is the pressure at the bottom of this lake? So we can use the liquid pressure equation. Pressure equals H rho G, 100 times 1000, that's the density, times 9.81. So I have 9.81 times 10 to the 1, 2, 3, 10 to the 5 pascals, right? So when I say the pressure is this 9.81 10 to the 5 pascals, what is this pressure? This is just the pressure due to the liquid. So we can say the liquid pressure due to the liquid. Now, atmosphere is pushing on this surface. The atmospheric pressure P0 is 1 times 10 to the 5 pascals. So we define something called the absolute pressure, P absolute, which is equals to PO, atmospheric pressure, plus PG, the gauge pressure. What we just calculated, this number here, is the gauge pressure, right? It's the pressure without the atmospheric part. On this planet, in open environments, wherever you go, we have the atmosphere around us. We are subjected to the atmospheric pressure all the time. So when we make measurements, most of the pressure meters are designed to measure the gauge pressure, the additional pressure above the atmospheric level, right? So what we calculate here, even in the calculation, what we calculated is the gauge pressure. If you want to find the absolute pressure, then you have to add the two numbers, so that will be 1 times 10 to the 5 plus 9.81 times 10 to the 5, that gives you 10.81 times 10 to the 5 pascals. So the reason I want to stay with this is sometimes PA can be seen as pascals, so let's not do that. We'll just stick with this P0. So the absolute pressure is the sum of gauge pressure, which is you calculate to find or you measure, and then you add the atmospheric number, you get the absolute number. Okay. So in that previous example, where we had a water tank 30 meters above the ground, and there's a house. This is the house. That pressure you calculated is the gauge pressure, right? We didn't consider the atmospheric part. We just use this height from the water level to the faucet. Okay, here's a low level faucet, outdoor faucet. We calculate the pressure using only the height difference. So what we calculated is again a gauge pressure. Okay, let's move on. So the next topic I want to discuss is the Pascal's principle. Principle. Now Pascal was a famous scientist, lived a couple of centuries ago, did a lot of things related to pressure and liquid pressure. So to honor this amazing scientist, we named the pressure unit after him. Pascal's principle, out of many equations, many theories he developed, there's one particular theory we're going to discuss. So think about a container that has two openings. So here's one opening, and here's a much, it's like two containers with two different areas connected together, right? So this is one single container has two different, two cylinders connected together. All right, that's easy. Now let's say we fill this thing with a liquid. So you put some liquid inside, so both sides it's gonna have the same levels, right? It's connected. Now what we're gonna do is we're gonna seal the two ends. So you're gonna seal this end with a lid that can be moved up and down. So we call these something like this a piston. If you're familiar with vehicle engines, you know what this is, right? So it's like, think about like when you're getting a vaccine, they use the syringe that has like some rubber piece that going up and down inside, something like that. So you can move this piston up and down by applying a force here. This side also we cover it with a piston, a movable lid. Now this is an enclosed liquid. Enclosed liquid is, in simple terms, let's say you have a water bottle and there's liquid inside and you close the lid. This is an enclosed liquid. So same thing here. Here we have two containers with different diameters and connected, and then there's two ends are covered with movable pistons. Now in this one more thing, let's say this side area is A1, this side's area is A2. Now here's an important thing. In an enclosed liquid, now this is something Pascal found out after a lot of experimentation. In an enclosed liquid, if you make a pressure difference on one side, right, you can apply a force like this. You can push down on this. Here you are pushing down, so let's say you are applying a force of F1. What's the pressure you are creating on this side? Pressure is given as force divided by area. So we can say pressure 1 on this side is force 1 divided by area 1. So when you create a pressure difference on one side and in one spot in an enclosed liquid, the same pressure difference appears everywhere in that liquid. So you're creating some P1 artificial pressure difference over here. The same P1 going to appear here. The same P1 is going to appear here. The same pressure acts on this piston as well, right? I shouldn't call it P1. Let's give it like a common name. Let's say P0. The same P0 is going to appear everywhere. So now what happens? This pressure is acting on the piston, and on the piston, similar to the pressure, it's going to create a force on the piston on the other direction, right? It's going to get pushed up. You're pushing down on this smaller side, creates a pressure. The same pressure is creating a force over here. That force is going to bring the piston up. So for the second side, the pressure can be written as F2 over A2. But we know that it's the same pressure P0. So these two has to be equal. So we can say F1 over A1 is equals to F2 over A2. This is very important. I'll show you why it's important in a second. This is called Pascal's principle. In an enclosed liquid, when a pressure difference is created, the same pressure difference appears everywhere. As a result, we can write this simple relationship. Now what's the application of this thing? Let's say here's this setup with two cylinders. One more time. This side area, let's say we have a small area of 10 centimeters square. This side here we have a larger piston, so the area is, let's say, 2000 centimeters square. Okay, so we're gonna push down on this side with a force of let's say 5 newtons. We know that this piston is gonna go up. The question is, how much force can we get out from this side? So let's do the math. F1 over A1 is F2 over A2. 5 over 10 centimeters squared should equal to whatever the force comes out over 2000 centimeters squared. Now ideally I should convert this into meter squares, but because both sides have the same centimeters, I'm not going to worry about it. Even if you convert it, the two numbers will have the same ratio. So what is our F2? F2 is 5 over 10 centimeters squared multiplied by 2000 centimeters squared. Even if I don't convert it into meters, the centimeters, the same unit's gonna get cancelled out. So I get F2 equals 1000 newtons. This is amazing. By applying 5 newtons, I can have an output of 1000 newtons, 200 times more. The amount of newtons, the multiplication, comes from the ratio between the two areas, right? A1 to A2 ratio. It's 1 to 200. 10 to 2000 means 1 to 200 area difference. So the force gets multiplied. So these kind of setups are very common wherever we use hydraulics, like hydraulic lifts, pneumatic devices that uses air pressure, in the vehicle, the brake, all these hydraulic brakes work using this. If you go to like an old-fashioned car wash or a repair place where they lift the vehicle, that's hydraulic lifts. Even in a lot of other machines, they use the same principle. So it's a huge advantage. By using a small force, you can get it multiplied. But it's not like really creating a new force out of nothing, right? The catch is, in order to lift the second side, let's say you want to lift it by 1 meter, you have to push the other side by 200 meters. It will have the same 1 to 200 ratio. So yes, you are getting more force, but on the other hand, the smaller side need to be moved a lot. So the amount of work you do is same. Small force, large distance, large force, small distance. But as humans, it's difficult for us to create large forces. We can walk long distances, right? So the distance is not an issue in most of the time. Actually, in industrial settings, the small side is actually not like a small cylinder, but it's like a long pipe or something, and there will be some kind of motor to drive this piston as long as it needs, and then you can get enormous force coming from the other side. So there are nice examples. It's a very useful application. Okay, so the next topic I want to discuss is how to use this liquid pressure equation. Now we already know that pressure of a liquid or a gas, the common term is a fluid, is given by H rho g. how do you use this equation to make measurements? It's very simple. We can use the liquid pressure to measure something unknown. How do we do that? Let's say we have a container, a gas tank or something, like a gas cylinder. So there's some gas inside, like for an example, oxygen. You guys use these things in your lab, in your biology labs also, different type of nitrogen gas or whatever. You might have seen that little pressure gauge attached to it, next to it, with a little calibrated like a scale next to it. So this is one type of pressure gauges. So that's one type. There is another type using liquids, actually can be considered as more accurate pressure meters. They are called manometers. Especially in industrial settings or even in medical settings, manometers are used to measure pressure. They last long, pretty accurate, less maintenance. Alright, so let's see how this thing works. So what we do is we take a tube and bend it to the shape of a U tube, U shape, and you pour some liquid inside. So since both ends are open, the liquid levels should be the same. And that's it. This is your pressure meter. Simple as that. Okay, so how do we use it to read the pressure? Now what we do is, one end, this end, goes to the gas tank where we want to measure the pressure. So let's say this is your gas tank and we don't have this thing. We take it, we connect it here, right? So here's the gas tank. Now one end is connected to that. Alright, so I need to redraw this diagram. Alright, so because of this pressure inside, and obviously this is higher than atmospheric pressure, so pressure inside is bigger than P atmospheric, right? So without the gas tank connected, so here's the tube, it was, both ends were open, liquid levels remain the same. Now once you connect something higher than the atmospheric pressure, this is going to push down on this side, so the level is going to go down, the level is going to go up on this side. So after that, what you would see is something like this. So here's the tube, connected to the gas tank. This side goes down, this side goes up, and this side is open to the atmosphere. So over here pressure is P0. Inside is some pressure X, which we don't know. Now how do we find the pressure? This pressure X, this amount is inside the tube, so where inside this right hand side of the tube, so up to this point it's Px. So right here where this interface between the liquid and the gas, the pressure is Px, so that means over here also Px. We know that in a liquid equal levels pressure is going to be the same. So if you draw a line connecting to the other side, at this level also pressure is Px. Now the left hand side, right, left hand side is all liquid. So this Px pressure, it's coming from the height of the liquid plus the atmosphere pushing on it. So if we want to know the gauge pressure of the tank, it's the height of the liquid column. So Px. We are just calculating the gauge pressure. That will be H rho G. H is this height. Rho is the density of the liquid. So you multiply the height of the liquid from the same level. You have to get the height. You draw a line connecting the two levels, right? The tank side to the other side, and then from that point you measure the height. Density is the manometer liquid, not anything inside the tank but the fluid in the tube. And gravity, that gives you the pressure, the gauge pressure of the tank, the pressure that is above the atmospheric level. If you want to find the absolute pressure of the tank, you add atmospheric pressure into this. Okay, so this is how you find the pressure due to a liquid. So the PowerPoint has some more information, different kind of pressure meters. I want you to go over them, take a look at them, see how they work. And in the next video, we will talk about some more new topics. Alright? Okay. Thanks guys.